A very good morning you all. Welcome to the video lecturer part 1 on heat transfer. So in this lecturer we shall discuss about the formulas, list of formulas in the heat transfer analysis by finite element analysis. Okay. So in the previous lectures we have seen the important derivations for heat transfer like 1D heat conduction, stiffness matrix for conduction, and Fe formulation of heat transfer, and 1D heat conduction, stiffness matrix for convection as well as internal heat generation. So in this video I have made a list of formulas which are very important when you are solving the problems. Okay, so here the very first formula, that is equilibrium equation. So this equilibrium equation, I think you might have seen in the previous lecturers in case of bars, beams, trusses, and even in the shafts. So in all the case studies we have seen this equilibrium equation because it is most important section when you are solving the problems. Before applying the boundary conditions, you have to solve for a stiffness matrix and assemble them, and you have to make a equilibrium equation. So this is common to all kind of questions or problems in the analysis of FEA. So in the previous cases of bars and beams, you have seen a different boundary conditions like and different equilibrium equation also. So in case of bar, KQ is equal to F, and here it is KT is equal to F. So nodal displacements and nodal temperatures are different for different applications. So there it was a displacement, now it is a temperature distribution as it is a heat transfer. So here K into T is equal to F is the equilibrium equation, where K is nothing but stiffness matrix, T is the temperature, and F as it is force matrix. And now stiffness matrix for heat conduction, that is one dimensional element of heat conduction, we have a stiffness matrix as AK divided by L, 1 minus 1 minus 1 1 in the matrix. So in the previous engineering problems we have seen for the bars it is AE by L, 1 minus 1 minus 1, and for truss it is different, and for beams it is different, and even for the shaft it is different. So similarly here the heat transfer application, this will be the stiffness matrix, that is AK by L, 1 minus 1 minus 1 1. And don't confuse with this K as well as this K. So this K is nothing but a stiffness matrix, and here alone this K is nothing but thermal conductivity of a given material. Okay, so that will be mentioned in the problems. And A is the area of the cross section, and L is the length of the given element. Okay, so now these two are common for each and every problem. Okay. Whenever you consider a circular object or composite wall, there will be conduction takes place, as you already know what is conduction, convection, and radiation, right? So conduction will be there in each material because it is an internal molecular movement of the objects, right? So but convection and internal heat generation, so these are the two different cases we need to study in this heat transfer analysis. So first let us see how the convections, right, how the convection formulas are. So now suppose here I have considered the two figures. In first figure convection is at the left hand side, but in the second figure convection is on the right hand side. So then what is the change you can observe in the formula is stiffness matrix. See, don't confuse with this K and this K. Okay, so this is the stiffness matrix for conduction. Okay, whenever the conduction is given in the problem, you have to use this equation. And convection, that to end convection, remember, end convection is given, then you have to use this formula. Stiffness matrix for convection, that is at the end. Okay, that is HA into 1 0 0 0. This is 0. Okay, So only at the left hand side it is given, hence you need to take 1 here. This HA will be at the left hand side, it means, okay. And in the similarly, next figure, here the convection is taking place at the right hand side of the given element. So here you need to take 1 here, okay, rest all are 0. HA 0 0 0 1, okay. I hope you understood the difference between the convection at the left hand side and the right hand side. Simply convection, if it is given at the left hand side, you have to take 1 here, and if it is given at the right hand side, 1 you have to take at the last element, last node you can say. So here H is nothing but the convective heat transfer coefficient. This is also mentioned, this is also be mentioned in the problems, and its unit is watt per meter square degree centigrade, okay. Now then when you are solving the problem, you need this equilibrium equation or condition, right? So here you need stiffness matrix, temperature values, and force matrix also. Hence the force vector due to free end convection. So don't forget this word, free end convection. Here the formula is AHT infinity 1 0. Why 1 at the first node is because at the node 1 we have the free end convection, H is given, that is why, okay. And same for this case, convection is given at the right hand side, so that's why AHT infinity as it is 0 1 you have to write, okay. Only change is that here it is 1 0, here it is 0 1, okay. It is not a big deal to remember this thing, right? Yeah. So where A is a cross section area, it is expressed in meter square, and T infinity, okay, one more term will be given at this end only. HT infinity data will be given for each of the problems, okay. So where T infinity is nothing but ambient air temperature, right? And this is applicable to composite poles. Next case is internal heat generation. For example, in the first derivation you have studied 1D heat conduction or differential equation for 1D heat conduction, where some amount of heat is supplied here and some amount is it is leaving out of the system, and some amount of heat will be generated in the system. In that case, okay, in that case you have to use stiffness matrix as PHL by 6 2112, okay. If heat generation is mentioned or not mentioned, that is not the matter, okay, no matter whether heat generation is given or not, that is Q value. If it is given or if it is not given, you have to use this matrix, that is stiffness matrix only. You have to apply this and get the stiffness matrix value, where P is nothing but perimeter of the given section. Suppose perimeter is nothing but it is applicable to a square other than the circle, okay. If it is a circle, we are using the term circumference, okay. Other than circle is given like square, rectangle, trapezium, in that case plane figures, you are referring it as a perimeter, okay. Now if heat generation is not mentioned, that is Q is equal to 0 given, you have to use force matrix, because in each and every problem you have to solve for K as well as F, isn't it? Because you need these two to solve the problem, okay. So that's why you need K also and F also. So this is common whether heat generation is mentioned or not mentioned. The problem is of this kind, you have to use this matrix only. And for the force matrix you have to use this value, HT infinity PL by 2 1 1, okay, when Q is equal to 0 given. And if heat generation is mentioned, that is Q is equal to some 100 watt per meter cube, 200 watt per meter cube, then you have to use the force matrix as this. If heat generation is mentioned, use the force matrix as this, and stiffness matrix is common to both the cases. So these formulas are very important to solve the numericals. In the next video, we'll see important problems associated with heat transfer.